Alright, today's an exciting opportunity to see the chain rule in great detail. It's going to be fascinating, it's going to be wonderful. Much better than cats. So chain, anybody know that quote?
I don't know.
Alright, chain rule intuition. How did we get a proof for the product rule? We built intuition by looking at simple functions. So let's consider the following. Let's let a of x be x to the fifth plus 1 squared is f of g of x. Okay? A prime of x, well, we can expand things out. A of x is going to be x to the 10th plus 2x to the 5th plus 1. A prime of x is going to be 10x to the 9th plus 10x to the 4th. And I can factor. And when I factor, I'll get 10x to the 4th, x to the 5th plus 1. Anybody know a better way of writing 10x to the 4th? Alright, we'll hold off then for a moment. I have f of x equals this. If I take f of x to be x to the 5th plus 1, and I take g of x to be x squared, then my function x to the 5th plus 1 squared, that's my f of g of x. Okay? So let's calculate some derivatives. F prime of x, oh I'm sorry, I'm doing it the wrong way. I want f of x to be x squared, g of x, is x to the 5th plus 1. And now f of g of x is going to just be x to the 5th plus 1. What's f prime of x going to be? If f of x is the squaring function, what's f prime of x? 2x. What's g prime of x?
5x to the
5x to the 4th. This looks a lot like what we have here. I've got 10x to the 4th, x to the 5th plus 1. X to the 5th plus 1, that's just my g of x. Right? What about my 10x to the 4th?
F prime of x times g prime of x.
Nope.
2 times g prime of x.
Okay, it is 2 times g prime of x. F prime at g of x is equal to... So f prime of input is twice input. F prime of g of x is just going to be
10x to the 4th.
10x to the 4th. So this is...
Usually f prime of g prime.
Yeah. I'm sorry?
F prime of g prime of x is f prime. Because if it's f prime of g x, it would be
Oh, good, good.
2x to the
Yes, you're right, thank you. Sorry. F prime of g of x, sorry, that piece, thank you. F prime of g of x is going to be 2x to the 5th plus 1, and then g prime of x is 5x to the 4th, thank you. And so now if I look at f prime g of x times g prime of x, that gets me what I want. So we see that this looks like f prime g of x times g prime of x. Is this a proof? Not quite sure what this is. The system is off.
Is the mouse touching that?
Could be.
This is light speed.
Up.
Alright. We've turned the volume down to whatever. I apologize for those of you who are sleeping. Is this a proof?
Well, this will wake up the people watching the video.
It will wake up the people watching the video. Yes, we're going for Oscar for Best Special Effects. Alright. Is this a proof of the chain rule? No. No. And again, there's so many ways to combine things. And in fact, one of the reasons I want to do this way was to deliberately make some mistakes. You can start putting things in. I can put in a g prime here and get my 10x to the 4th. There's lots of ways of getting things. The problem is this exponent is not high enough. what should I really do instead of having a square? I'm sorry? A cube, or fourth. Take a higher exponent. Then it's going to be a little bit more work to expand, a little bit more work to simplify. So as a nice exercise, replace the 2 with a 3. Have something a little bit more involved and try to build even more intuition as to what's going on. Alright, this is showing you that it's consistent, but maybe this was supposed to be f prime at g prime. And that would have given me a 10x to the 4th. So again, with small things it can be very misleading as to what's going on. What I want to do now is say, well, we've at least seen that the chain rule is reasonable. That maybe it should look like f prime at g of x times g prime of x. And now I want to give you a proof in one dimension. So proof in one dimension. Alright, so for the proof in one dimension, we let a of x be f of g of x. What is step 1 in every proof of every differentiation rule? Step 1 is always the same. What do we do? Yes?
The definition of a derivative.
Definition. A prime of x is the limit, as h tends to 0, of f of g of x plus h minus f of g of x over h. And so I really should be writing a of x plus h and a of x. I'm just saving a little time. So really, a of x plus h, and really, this is a of x. Alright, so we want to try to figure out what's going on. If instead of having g of x plus h, imagine we had f of g of x plus h. I move the parentheses inward. I can't, but imagine I just moved the parentheses inward. If I move the parentheses inward, I've got f of g of x plus h minus f of g of x over h. What does that look like?
It's the limit of f of x. If g of x plus h over x.
Not the limit of f of x.
G of x is the x in this.
So g of x would be the x. If I could do this, which is illegal, what is this going to look like? It's going to look like what? So if you want, call this, say, f of a plus h minus f of a over h. It's going to look like
Derivative of f of x.
the derivative of f at a. Okay, so if I could just move the parentheses inward, it would be f prime at g of x. That's close to what the answer is. It's not exactly what the answer is, but it's close. Okay? So this suggests an idea on how to proceed. We can begin to see the f prime at g of x from here. So if I look a little bit more, this is the limit as h goes to 0, f of g of x plus h minus f of g of x over g of x plus h minus g of x times g of x plus h minus g of x over h. Why am I allowed to do this?
You're multiplying by 1.
I'm multiplying by 1. Am I allowed to multiply by 1?
Yes.
You have to be careful.
Only if h doesn't equal 0.
Not h, because h is never 0. Yes?
If g of x plus h minus g of x.
Yes, if g of x plus h minus g of x equals 0, I'm in trouble. Because then I've multiplied by 0 over 0. Well, if g of x plus h minus g of x equals 0, that means g of x plus h equals g of x. I'm not going to go into all the details. If that only happens finitely many times, I'm okay. If it happens infinitely many times, I'm in trouble. Well, the only way it could happen infinitely many times would then require g prime to be 0. And again, if I look at what's going on here, if g of x plus h equals g of x, the numerator is 0. So I'm not going to go into the details as to what happens if g of x plus h equals g of x infinitely often as we get closer and closer and closer. It's a little bit more work, but if that happens, you then get g prime is 0, and this is going to be 0 as well, so you get 0 equals 0, you're okay. I will assume that for h sufficiently small, g of x plus h is not g of x. So I can multiply by 1 like this. I have a limit of a product. What is the limit of a product? Product of the limits. And now, I have the limit as h tends to 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x times the limit as h goes to 0 of g of x plus h minus g of x over h. One of these two limits is significantly nicer than the other. Which limit is the nice limit? Yes?
The one on the right is
The
just
one on the right, yeah. And it's just,
the derivative of g of x.
good. This is just g prime of x. What about this one? So this is a bit more involved, but remember, we saw another way of writing the derivative is f prime at x naught is the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. This is the alternate definition of the derivative. If you let the point g of x be a, I'm taking the limit as another sequence of points goes to a. By the definition of the derivative, this is just f prime at g of a. So it's the other definition of the derivative. So using the limit as, I need a new variable, I'll say t goes to a of f of t minus f of a over t minus a equals f prime of t, we get f prime of g of x times g prime of x. And that's the chain rule in one dimension. Right? So what I hope you got from all of this is that the chain rule is reasonable. You know, we started off, just like the product rule, by looking at a special case where we could compute things directly. The special case was not the greatest. And so we really should do the case of a cube. I leave that to you as an exercise. We then went through and we had an idea we should be getting an f prime at g of x times a g prime. That gave us the idea of multiplying by 1 in this way to get a derivative of f at g of x. And then it was just, algebra and limits from this point onward. Okay. Any questions about the proof of the one-dimensional chain? Yes?
I didn't get, why does the h turn into g of x plus h minus g of x?
Why does the h change? The h just moved over here. The h just walked down. So it's all about how do you group things. And that's why I wanted to do this, example, this illustrative example in the beginning to try to give us a sense of how to group things. I want the g of x plus h minus g of x over h. So I want to group things like that. The chain rule is the hardest of all the proofs. So in the course notes that you can download, I have, I think, 6 pages. This is sadly before I learned how to use LaTeX. It's done in Microsoft Word from the late 90s, back when I was a grad student at Princeton. So I apologize for the formatting, but it goes through very slowly how you would prove the multivariable chain rule in several dimensions. And so I'm not going to do the proof in class of the chain rule for several dimensions. We've done the proof in one dimension. I'm going to try to show you how to use it. I hate the book's notation here, and I don't mind if this is recorded. I think it's very bad notation. I think it's very confusing notation. One of the reasons I don't like the book's notation is it kind of hides the fact that the chain rule is about composition of functions, and it hides that we have compositions of functions. And so, I think this is real dangerous. So, chain rule, several dimensions. So let's say we have W of UV is f of x of UV, y of UV, z of UV. Right? So I start off with the function f. How many inputs does f take? 3. And how many outputs does f give you? 1. F is a real valued function. I can now view x, y, and z as functions. How many inputs do they take? how many outputs do they give you? And last and least, how many inputs does W take? And how many outputs? 1. Okay? Sometimes it's nice to introduce a new function. G of uv is G1 of uv, G2 of uv, G3 of uv. And then you could write W of uv is F composed with G of uv. Then you have a chain of functions. Okay? The book completely hides this notation. Now in this situation, what would the function G1 be? G1 of uv would be X of uv. G2 of uv would be Y of uv, and G3 of uv would be Z of uv. So I'm telling you, I want some functions that depend on other functions. For example, maybe x equals r cosine theta, y equals r sine theta. And maybe z is always equal to 1. And so now my variables u and v, I would now be using r and theta. Why would I use r and theta rather than u and v? Does it matter what letters I use for the variables? No. If you have a circle, what are you used to using for circles? R and theta. So if I'm giving you a circle, I would probably use r and theta and not u and v. If I was using a sphere, I'd probably do rho, theta, phi. Okay? So depending on what I'm giving you, I would use different letters. So here is the statement of the chain rule. We want to calculate how W changes with U. So if you think about what this means is, I take W and I increase U by a little bit. And I want to see how things change. And so the chain rule says that this is equal to df dx dx du plus df dy dy du plus df dz dz du. So this is where things become an absolute nightmare of notation. And as bad as it is for you, I have to do this again at 11. Alright? So x in some sense is pulling double duty. It's both a variable, when I regard f as a function of 3 variables, and itself it's a function of the 2 variables u and v. So what I'm really saying is, look at how f changes with respect to its first variable. And then see how that variable is changing with respect to the variable u. What do you think dw dv would be? Search and replace. Right? All I do is df dx dx dv plus df dy dy dv plus df dz dz dv. It's very important that you write partials here and not full letter d, that we're not doing a full derivative. I want to know how my function changes as I change other things. So this is compact notation, and it's hiding a couple of things. When I give you a function, you need to know, where do you evaluate the function? So where do I evaluate df dx? Where do I evaluate df dy? Where do I evaluate df dz? Where do I evaluate dx du, dy du, dz du? So I evaluate these at the point uv. And where do I evaluate df dx, df dy, df dz? At g. And in fact, that's one of the reasons why I like introducing the g function. Because that tells me that's the point I evaluated. I evaluated a g of uv. So this one, and this one. The other ones are all at just the point UV. Okay? So you have to remember where things are. Let's check and see what would happen. If we only had f as a function of one variable, and if that variable was only a function of one variable. So imagine a world without any v's and without any y and z's. So if there are no y and z's, we lose these last few terms. And we get dw du is df dx dx du. Basically, dw du is f prime at g times g prime. So in the special case when we don't have a y or a z, and we don't have a v, this does reduce to the one-dimensional chain rule. One way to view what's going on is, if I increase u, how can the function w change? Well, if I increase u, that changes x, y, and z. Right? So changing u increases x, increases y, increases z. So if my function x increases, if I'm changing the point where I evaluate at, that's where my df dx comes from. That's where my df dy comes from. That's where my df dz comes from. This little bit over here is to try to give you an understanding of, if I increase u by a little bit, how much does x increase? If I tell you x increases by 0.1, we talked last class about how to translate that, using the tangent plane, into how the function changes. Well, if u increases by 0.1, does x increase by 0.1? Not necessarily. I need some way, I need some kind of conversion factor. So if you want to think about this as, changing your dollars to euros or something like that. I want to know, if I increase u by a little bit, how much does x increase by? Because when I'm doing this tangent approximation, I need to know how much has x changed. And when I want to see the change in f, because of the x-coordinate, I need to know how much the x-coordinate changed by. Well, if I increase u by a little bit, dx du tells me how much x changed with an increase in u. And that's what I then feed into the tangent from last time. So again, this is where I'm trying to use the fact that you have watched the video for this lecture, where I've talked about the chain rule. I'm trying to talk about things differently than in the lecture to give you two different perspectives on the subject. It's basically chasing things around. I want to see how the change propagates. So going back to the linear approximations from last class, going back to the tangent plane, we saw how well we could do by translating small changes in the variables to how the function changed. And we had this little change, time elapsed, the x minus x naught, the y minus y naught. That's what these pieces are. Okay? Can I cancel the dx over here and just say that this is df du? No. If I could do that, imagine I could cancel like that. Hump, hump, hump. Right? Oh, I get df du 3 times. Right? That's absurd. Right? Also, f is a function of 3 variables, not a function of 2 variables. F is not directly a function of u. I am a big fan of killing trees. Not for no reason, but put down plenty of text to really anchor you in what you're doing. It's very easy to get confused in something like this. Spend the time, write a little bit more than you need. Okay, I apologize, the chain rule will not be on midterm 2. Nothing on midterm 2, which is next Friday, will include anything from today. It's only up until last class. But when we do derivatives, this is a great way to review stuff. Okay? So over here, this is my statement for the chain rule. This is where I evaluate everything. And again, if I have a function f, I have to evaluate f at a triple. I can't evaluate df dx at uv. It makes no sense. F is screaming for 3 inputs. I have to evaluate it at this triple, x, y, z of uv or g of uv. Okay? The book has horrible notation where they'll say w is w of x. They'll use w on both sides. I don't like doing that. For me, f is a function of 3 variables, w is a function of 2 variables. They're not the same function. The book will often overwrite things and say, well, screw it, let's just use the same letter on both sides. I think this leads to confusion. Remember where things are. I think I will give you some homework problems on the book's notation, just so you can show me that you've suffered through the book once. On exams, I will only give you stuff using my notation. Okay. But you should be aware of other people's notations. Question?
G1, G2, and G3 are all different functions though, right?
Probably. They could be the same.
Oh, they could be.
They could be the same.
Yeah.
I'm just giving them names G1. Maybe x of uv is 5, y of uv is 5, and z of uv is u squared plus v squared.
Yeah.
I don't know what these functions are yet.
But, so they're not necessarily.
They're not necessarily. Okay, so this is the statement of the chain rule. Are we all comfortable with the statement of the chain rule? Alright, I'm going to show you the flow chart. So, amazingly, I never saw this flow chart until I came to Williams and started teaching the subject. And I do think the flow chart is nice and a good way to try to remember what's going on. So I have a flow chart. So we have the following. W of uv is f of x of uv, y of uv, z of uv. Now, of course, if I had 4 variables instead of x, y, z, I would use. If I had 4 variables, w, x, y, z, or x1, x2, x3, x4. Cameron was doing a math problem with me, and I'm teaching him variables, so he was using the letter A as a variable. I said, okay, we need something to come before that. What should we use? And he said Z. I was very proud. He earned an M&M for that one. Okay? But again, we run out of letters quickly. And so if I have more things, I would use x1, x2, x3, x4. What if I had more than 2 variables in uv? I could do uvw, but eventually I'll do u1, u2, u3. Right? I'm trying to write x, y, z, and u and v to make things a little friendlier. Right? So we have some function w. W depends on 3 variables. X, y, and z. And x, y, and z depend on variables u and v. Okay, so this is the flow chart. So going from here, this is df dx, df dy, df dz. Bless you. Over here, this is dx dv, this is dx du. This is dy du, this is dy dv, this is dz du, this is dz dv. And so you make a chart like this. You start over here with your function, and then your function, your w, this is our f of g of uv. So in the first row, well, I guess the second row, this is the first row. In the next line, you put the variables that f depends on, x, y, z. In the next one, you put the variables that the x, y, and z depend on. And you draw an arrow to indicate how you can move. I can go from w to x, w to y, w to z, and I can go from x to u or x to v. And if I want to figure out what is dw du, dw du is I look at all the ways to get paths that end in u. And every time I have an arrow followed by another arrow, I multiply. So then I would get dw du would be df dx dx du plus df dy dy du plus df dz dz du. And so some people find this as a useful way to remember what's going on. And you just draw the picture and look, how many ways can I get down to u? Every time I have an arrow following an arrow, I multiply what they have. Do I need to calculate df dz, dz, dv? Not if I only want to get dw du. Okay? And then we can talk about what is the gradient or what's the derivative of w. So the derivative of w, or the gradient of w, is just dw du dw dv. Okay. On the first exam, you might have noticed there were a couple of problems where if you used your favorite New England transcendentalist writer, the problems became a lot easier. On the chain rule, if you do not mind, I will give you problems where you can bypass the chain rule and do things directly. Okay? However, you will still have to do it using the chain rule to receive full credit. Okay? Why am I doing this?
So that we know the chain rule.
So that you know the chain rule. But why would I give you something where you can bypass the chain rule?
You can check your
So you can check your answer. Okay? I want you to show me that you can do the calculation. So let me do the same problem that's in the notes. So let's consider the function w, and I use the book's notation, which I hate, is x cosine x squared plus y squared with x equals r cosine theta, y equals r sine theta. Okay? So this is extremely confusing notation. When I write w equals this, what is w a function of? Is w a function of x and y? Is w a function of r and theta? I really, really hate this notation. Okay? It's confusing to look at. So a lot of times, when you see something that's stuff like this, so let's do slowly. W of r theta is going to be f of x of r theta, y of r theta. So f of xy is x cosine x squared plus y squared. What would w of r theta be? Well, x is just r cosine theta. And now I have x squared plus y squared. What's x squared plus y squared?
R squared.
R squared. Do we need to use the chain rule? If I want to calculate dw dr, do I need to use the chain rule? Can you find dw dr without the chain rule? Yeah. Just take the derivative. So dw dr would just be, okay, so first take the derivative of r, so I get 1 times cosine, oops, there's no for this, cosine of r squared plus r, and the derivative of cosine is minus sine of r squared, and then the derivative of r squared is 2r. So for those of you who are pausing as to, do I need to use the chain rule? If you are pausing because we have to use the one-dimensional chain rule, excellent use of the pause. We don't have to use the multivariable chain rule. But when I have something like the cosine of r squared, we have to use the chain rule. Do you guys know the English trick to detect chain rule? The English trick is the word of. Almost always when you hear the word of, chain rule is happening. I have the cosine of some function that, you would never say I have the cosine of x, unless you're trying to put on real literary ears, and most of you probably will not be doing this in math, right? I won't ask if you've written math poetry, but if you're trying to do something like that, and you need that extra syllable, maybe you'll say, there once was a cosine of x. Okay? Other than something like that, okay, you're not going to be putting in the word, this was done spur of the moment. I'm afraid to continue. Other than that, you're not going to throw in the of. Okay? But would you say cosine x squared? Does that sound right to say, I have r cosine r squared? Would you say r cosine of r squared? I think the of sounds a little bit more natural. And so when you hear of, you should think chain rule. Another good word to remember in English is the word to. I have 3x plus 5 to the 8th power. What does to imply? Power rule. The power rule is actually just a special case of the chain rule. The power rule is the special case when the function f of x is x to the 8th or x to the n, something like that. So whenever you hear the word to, that's basically the power rule, which is actually a case of the chain rule. Right? So now I have my dw dr. I could calculate dw dr the long way. dw dr is df dx times dx dr plus df dy dr. And the difficulty here is I have to remember where do I evaluate everything. So what I want to do now is I just want to go through everything very slowly and just do the example with great care. And then we'll see that hopefully that it matches up and agrees with what we have. So continuing, df dx. So if I look at what's going on, what is df dx going to be? So I will have the function f of x is x cosine x squared plus y squared. So the first is I take the derivative with respect to x, so I get 1 times cosine x squared plus y squared plus x. Now I have to take the derivative of cosine of x squared plus y squared, so it's going to be minus sine of x squared plus y squared, and what's the derivative? Times 2x. Do I want df dx at the point x, y? Where do I want df dx? At what point? So I want df dx at the point x of r theta, y of r theta. Okay? Alright, so now the first place just becomes cosine of r squared cosine squared plus r squared sine squared. And that's just, so r squared cosine squared plus r squared sine squared is just 1. Not 1. R squared cosine squared plus r squared sine squared.
R squared.
R squared, right? Because I'm now just replacing x with our cosine theta, y with our sine theta. So x is our cosine theta, y is our sine theta. Now I have minus 2x squared, so that'll be an r squared cosine squared theta, and now I have a sine of r squared. So that's going to be df dx. Okay. Now we calculate df dy. And so a very similar calculation. Oh, crap. Okay, so now we have df dy. It's similar calculation, but it's actually a little bit nicer because we don't have the y dependence outside. So we're going to just get minus x sine x squared plus y squared times 2y. So df dy is going to be minus r cosine theta times sine of r squared times 2r sine theta. And so if you want to simplify that a little bit, it'll be minus 2r squared cosine theta sine theta sine of r squared. We're not even about halfway done. All right, we've at least done the harder part. Are you beginning to see direct substitution is better here? Okay, so now let's continue. So now what do we need? So for the next part, we need to figure out what is dx dr, what is dx d theta. So we get dx dr, well that's not too bad fortunately. Dx dr is just, what's dx dr? So x is r cosine theta, y is r sine theta. What's dx dr? Just cosine theta. What's dx d? Oh, and we're doing, sorry, we need dy dr. What's dy dr? What's that? Sine theta. I wanted to write down dx d theta. I like to calculate dx d theta, but do we need it for this problem? No. So now all we do is we substitute everything back, and so we get dw dr is df dx dx dr plus df dy dy dr. If you'll notice, we spent a lot of time when we were calculating things, evaluating things at the final points we needed. The reason is now we just have to substitute into our table. This is the way I like to do my integration by parts. I like to calculate everything ahead of time and then just build it in together. I like to have my table complete. So now I look, oh, I've calculated df dx. Df dx is this monstrosity. So I get cosine of r squared minus 2r squared cosine squared theta sine of r squared. And now I multiply both of these by cosine of theta. And now I have df dy, dy d theta. So I've got a minus 2r squared cosine squared theta sine of r squared times sine of theta. Okay. So hopefully we haven't made any mistakes. Does this look pleasant? No. Not even close. Right? And so we've got all of the different pieces now. And so a lot of the cosine terms are supposed to vanish. So let's see if we've done everything correctly. So we start off with cosine of x squared plus y squared, x, 2y. I have df dy. Wait a minute, I think I wrote the wrong thing down here for df dy. I wrote the wrong thing for df dy. Df dy is supposed to be minus 2r squared cosine theta sine theta sine of r squared times dy dr, which is sine of theta. Alright, so if we look at what happens, these both have a sine of r squared. We have a cosine theta, minus 2r squared, minus 2r squared. Cosine squared plus sine squared is 1. So this simplifies to cosine of r squared minus 2r squared times 1 times sine of r squared. Does that match what we had before? Yes. We can put a check mark here. All right, it matches. Does anybody prefer doing it like this? Okay, good. Not one person prefers doing it this way. It's nice that we can calculate the answer two different ways, but we don't want to do the calculation like this. So the question is, why do we have the multivariable chain rule? Why don't we always directly substitute? Sometimes we don't have nice explicit versions of the functions, so we can't directly substitute. When we get to Lagrange multiplies, which is essential in terms of trying to understand optimization theory, we're not going to have explicit closed form expressions. So we won't be able to do things directly. Okay. Other times the direct substitution is going to be very complicated. It'll sometimes be a lot easier to calculate these various quantities and put them together than to make this one massive, extremely complicated function. Yes?
So how did you simplify to the last step? Did you...
So they both, this term and this term, they both have a minus 2r squared.
Right.
They both have a sine of r squared. And this is a cosine squared, cosine, do we have an extra cosine theta? Do we? Did we make a mistake somewhere? Okay, so it looks like there's an extra cosine of theta over here. Let's see, if we look back at what we had initially, we have x cosine of x squared plus y squared. Oh, did we drop something? Oh, we made a mistake in the initial. Good. I wish I could claim that was done deliberately. Sadly, I cannot. Beautiful. So Yeah, thank you. All right. Well, we went from here to here. Do we have the correct thing for W? So it's better. All right. There we go. All right. Nobody caught this mistake, sadly. All right. I wish I could say this was done on purpose. All right. All right. If it's not working here, what did we do wrong initially?
X should become r cosine theta instead of just r.
X should become r cosine theta.
I was kind of confused by that.
And you should have spoken up.
Oh,
I thought I was
okay.
wrong.
No, you should have spoken up.
Here.
Right?
It's tilted.
It's tilted. It's fine. It's the end of the day. So this should not have been r cosine. We should have had. Oh, and I originally had a theta, I think, and I erased things. I had written cosine theta and then I had erased it. So this should be an r cosine theta looking. And so now when I take the derivative, we should have a cosine theta over here. And then over here, we should also have an extra cosine of theta. Alright? You know how many M&Ms you could have saved? So now when we go over here, that's the extra cosine theta, and everything now works. So, while unfortunately this has now been recorded for posterity, the algebraic mistake I've made, this really drives home why we care about the chain rule. You know, not one person spoke out that, hey, we've made an algebra mistake here. If you can compute something two different ways, this is the advantage. Hey, the answers don't match. I don't know which one is right, and in fact it's possible both of them are wrong. But I know at least one is right, and maybe this one is right into here, and this one is right here. Oh look, I had some algebra mistakes here which I fixed, then some algebra mistakes here that I fixed, and eventually they converge to the correct answer. Okay? This is one of the advantages of the 11 o'clock. Now in fact, I deliberately wanted to record the 10 o'clock today and not the 11 o'clock. Precisely because of stuff like this. This is actually a good thing. Okay? This is one of the powers of being able to compute things two different ways. You minimize your chance of making a mistake. The best thing to do is to have two separate pieces of paper and do the calculations like that. So you have the formula for the chain rule. All you have to do is figure out what functions they are, how they're chained together, calculate the different things, make the table, do the substitutions. If you can substitute things in directly and correctly, then you can do the calculation as well. Is that calculation going to be faster? Almost surely. Okay? Now, there will be times when you won't be able to do that, but it will still be a great way to check what's going on. Okay? Any questions on the chain rule? Okay, you can get a little merit badge that says you survived the chain rule lecture. Okay? This is probably the worst lecture in terms of content for the entire semester. Okay? The chain rule is extremely important, but in terms of content, it's very painful to go through. Alright, congratulations.